And similarly, why you can look at concrete that's 50 years old that looks like this, and then concrete that's like 7 to 10 years old that looks like this. That's going to be a lot of what we're going to try and cover today is what's going on. So what is concrete? There's 3 parts to concrete, and there are 3 parts aggregate, 2 parts of smaller aggregate, and 1 part cement or paste, or what's known as fines. But before we get into that, we'll talk about lime cement quickly, just because lime cement concrete was around. More it was used in mortar, but also there were in very, very old buildings, there are concrete floors that were made with lime cement and aggregate. So we're going to quickly cover lime cement and how it works, because it is a component or an element in our modern concrete. So lime cement is, of course, made from lime, which is limestone or shells, or actually that's a redundant statement because limestone is coral and shells that have become sedimentary rock or limestone. So it's pretty much a redundant term. This is hydrated lime, or what's called carbon hydroxide. And this is the lime cycle. So we're going to go through this really quickly just to make sure you understand it. If you've ever seen a bag of lime that has become really hard, one big block, some of you guys, this is redundant, but you want to automatically think that it's because it was exposed to water, but it's actually just the opposite. It was exposed to carbon dioxide. The plastic liner of that bag was keeping moisture in. Carbon hydroxide, the hydration that's in the carbon hydroxide, is locking out calcium carbonate, which has been driven out through heat in this first part of making hydrated lime. So the heat drives out the carbon dioxide. It becomes what's called carbon oxide, which is now it has no carbon dioxide in it. Then when you hydrate it, that locks that carbon dioxide out. It can't get back in, but it wants to. Nature wants it to return to limestone, kind of like magnets attract us, the same thing. So when you finally lay up mortar or pour lime-based concrete, slowly as it dries, through carbonation or rejoining of the carbon dioxide to the carbon oxide, it becomes again limestone. And that is the whole process of how it becomes either concrete or cement. So the modern cements are hydraulic, and they set underwater, and actually water begins that process. It's a little bit different in how that works. But to try and explain it, this is your large aggregate, your gravel and concrete. And then you add sand to that and cement. And what you're trying to do is each of the things you add is filling in the voids left behind by the other larger material to get something really dense. And I took this picture because this is an incredibly dense concrete. That's about as good as you'd ever want to see. That is some solid concrete there, and I bet it was no fun cutting through that. So again, this is what you have is the elements, and water is critical in concrete, more critical than you realize. So we're going to go cover that now. So how modern concrete sets is through this. This is the lime cycle, but also these there are certain things that are added that will cause the majority of the concrete to set through hydration, and it starts forming silicates. We'll cover that in just a second. A portion of it continues with the lime in it to go back to limestone, but the majority of it is going to set through a different process, and that's through hydration. In other words, the water is what's starting the setting process. So lime-based materials, they set over a period of time, and it can be decades to even centuries. Because keep in mind, if it's like a 4 or 5 white brick wall, carbon dioxide's got to get to that carbon dioxide that's in the center of that wall. And it's not easy for it to do that, so it takes forever. And that's why lime mortars, for instance, can self-heal, because every time a crack forms, some of that lime moves out with water, gets exposed to carbon dioxide, and sets in the crack. And that's why there you have that self-healing process in lime mortars. And that also happens with the lime concretes. So again, modern cement, it's that sets through hydration. And this is kind of lead us into the slump test, but you want your concrete when you're mixing it as dry as possible. In fact, the Romans, they were actually ramming the concrete into forms. They'd have it very dry and tamp it in. The more water, the weaker the concrete. So, and that's what the slump test is trying to determine, is how strong the concrete is in terms of and it's all based on water. The more your drier concrete, as long as you can get rid of voids through either ramming or vibration or something, that's your ideal situation with concrete. And the wetter it gets, the weaker it starts to get. But right here in this little sweet spot is where it's going to be the strongest, where you have a good high compression concrete. So when you add the water, and if you get to where you're adding too much water, what happens is that water that's in there becomes voids. And those voids are the weakness. That's what becomes the weakness in concrete that's too wet. You want to try and avoid that. And there's a couple things that will help you avoid that. One is, of course, trying to avoid putting too much water to it. But the other thing is, I'm going to lead into these. This is the slump test, and this is what it's testing for that water. But has anyone ever seen this before, this pattern on concrete? Okay, well, what do you think that is? Anyone? It's burlap, right? It's not an anti-skid deal. It's when I was a kid, they were doing this all the time. But they back in the day, in the 30s and 40s, concrete technology was at really an apex, and people were really pretty detail oriented. So when they poured concrete, they would put burlap on it, and they would keep that concrete wet for a week. And that's how you get good, strong concrete, because those voids that are going to, through evaporation, become just that, voids. If you keep the water in the concrete, instead it becomes silicates, or silicates start developing. It's a kind of a miraculous process, but the concrete gets denser and denser and harder. And so when you don't cure the concrete, you lose all that, all the silicates that are going to form. There's like 3 or 4 or 5 different silicates that are forming, that are filling in those voids and making the concrete extremely hard. So curing is, it's really important, but no one does it. And that's what this little process here is that curing process going on, where it's developing all those silicates. That's what, when you don't cure your concrete, that's exactly what you're losing. I show this because, believe it or not, that this is the Hoover Dam under construction. There is not one rebar in that whole dam. That's all monolithic concrete poured in little blocks, as you can see, all formed. It's solid concrete. It's like a puzzle. And it's what's called a gravity dam. But again, I want to reiterate, no steel in it. And we're going to find out that steel is not good for concrete. They don't work well together. At first they do, but this dam will be around for thousands of years because it has no steel in it. That's a part of why it won't fail. But during this process of setting, that setting process generates a lot of heat. And when you pour as much concrete as they were pouring, as fast as they were pouring it, that heat has no place to go. And they knew this. And you also have to have ideal temperatures when concrete sets. And so they were going to have temperatures that were way too high here. So they actually were pumping water through the concrete, through tubes, to keep the concrete cool. So that's how detail oriented and scientific they were about building the Hoover Dam. They understood what it all meant as far as what could happen. But back then, but again, between the 40s and 50s or 30s and 40s, they understood this principle so well that even with house or residential footings, they would either water cure or earth cure the footings. In other words, they wanted to try and lock that moisture in so it could do all of that setting that was possible if you didn't let the water evaporate out. Again, they don't do any of this anymore. They just pour the concrete and go. The unfortunate part about that is when you do these PSI tests, if you're doing a PSI test and you send that cylinder off to the lab, they're going to hydrate that cylinder for a few days before they test it. So if that cylinder is hydrated before it's tested and the concrete in the field is not cured, what's the cylinder telling you about that concrete out in the field? Yeah, it's basically like shocking a well. It doesn't really tell you anything. The well still could have a problem. But now we're on to footings. Footings, they always have to be installed on undisturbed soil. That's extremely important. And they should be poured all at once. You don't want cold joints. And this was a concrete that was out in Arizona and looked at this footing being poured and they stopped right in the middle of a pour. So I guess they were okay with cold joints for this particular footing, but you just really shouldn't do that. Under the footings, and when I say undisturbed soil, there's an angle of repose. You're trying to avoid cutting into that 45 degrees under the bottom of the footing. And in fact, in reality, every soil or media that you have a footing on has a different angle of repose. So this is going to move depending on what it's on. I'm sure on bedrock, it could be just like that. Sand is going to be way out here somewhere and it would have to be wider. But the 45 degrees is the rule of thumb for that angle of repose that you don't want to cross into. So here are one of those cylinders, and Martha and I, we did a commercial inspection where we got to walk through one of those labs. It was just sheer luck, but I looked into that room where they had all those cylinders curing, and the room was just being pumped full of mist. So all these cylinders were being kept really wet, and then it made me think, boy, there's something wrong here, because I know that the concrete out in the field is not being cured like this. These are all of the requirements to do proper testing for PSI rating on concrete. And it's, I really show you this to underline again that, well, this might be happening to the concrete being tested at the lab, but that's not the conditions that the concrete out in the field is under. Moving on to flat work itself. When you have concrete and you pour it really flat, you don't have any slope to it, it's going to stay perpetually wet. And that's not good for concrete because the porosity is going to allow moisture to set there. And then freeze-thaw cycles will be much harder on the concrete. It's got to drain. And it's even worse if you have convex surface where water stands. That's worse yet, because you're going to have not only saturated concrete, but then you've got slippery ice on top of it, but also your chances that the concrete is constantly being stressed by freeze-thaw cycles in all the pores of the concrete, it's going to accelerate the failure of your concrete. So in fact, really, when there's ice on the concrete or standing water concrete, I always put in something like this, basically saying, hey, you know what? In the wintertime, if nothing else, this can be dangerous. So be careful. Know that this might be okay when you're walking on it in summertime, but if there's ice on there, it could be dangerous. So ideally, you want all your concrete to slope or to be crowned. A lot of times you'll see in concrete on the highways, they crown them, and you can feel it when you're trying to drive on a highway that's crowned. It wants to pull you a little bit right and left, but that's because it's crowned. They don't want water on there. And in fact, that's really why they groove concrete. It's not for traction. Well, it is for traction in a roundabout way. It's trying to make sure that the water has someplace to go other than hydroplaning you down the highway. And it just makes it easier for it to disperse water under your tires. So again, we're back to curing the concrete. And if you don't cure it properly, this is what you get. So we're going to go through a series of pictures here. So again, this is kind of a recap. The things that can cause this, there are many of them. One is very flat concrete that's not straining, too little cement, too much water. When it was poured too wet, and then not properly cured. All those things will weaken the concrete. Yes, sir.
What do you label that as? What word, like alligatoring, or is that different? But
Spalling.
spalling. Okay, got it.
Yeah.
Yeah, thank you.
Each one is a little different, and it's always hard to decide what single factor or what combination of factors causes this, but it's usually one or all of the things I've just mentioned. This is just quickly touching on masonry for just a moment. And this is just when you have pavement that's installed on just stone dust or something like that, the proper way to do it. And when you put in masonry units on stone dust or something, you should really use a plate tamper and tamp them into place. You install the final product a little high and then vibrate it down into place. So this is a concrete porch, solid concrete porch. And as you can see on the right, it's solid and concrete's heavy. This isn't very old. It's probably, 1 or 2 years old, and it's already sunk down about 2 inches because it's probably not on good soil. But that's a lot of weight. Also, you want to make sure when you pour something like that, that you are not on backfill, and they break this rule a lot. Because if it's not on compacted backfill, it's going to sink and rotate like that. About the only thing you can do to avoid that is to tie into the masonry foundation. I think I've got that picture coming up in just a second, but this is concrete poured directly on the ground, same thing, up against the house that's on backfill that wasn't compacted, and so it's rotated. Here's a porch, same way. They just poured a concrete footing up to the house, but didn't bear into the masonry. And so because it's not a compacted backfill, it sunk. About the only way around that is this, to take a concrete lintel, lay it on a footing that is on compacted back or on undisturbed soil or very well compacted backfill, and then bear it into the building itself. So this is something I write almost every day, and this is one of those battles I have with builders that they never listen to, and they always insist that it doesn't happen on their house, and I'll see their house in 5 years, and it happened. They'll fill these big porches full of gravel, and they claim that gravel is zero compaction, which maybe from an engineering standpoint it's supposed to be, but still the concrete settles, and it almost always rotates towards the house in a few years. And then you got to use concrete jack to pump it up. So here's one, like I said, this builder said, "Oh, it never happens to my house as well." Within a week or so, I saw one of his houses, and sure enough, it had happened. And it just keeps going on. It gets worse. But you can, of course, you can pump this back up, but it's so easy to avoid this problem. You either have to go ahead and pour the concrete originally into your stoop, either in through open cores, or just build it a little larger so that it has a ledge for it to pour onto. It really costs nothing to do this, but builders never listen to me. They always insist upon the fact that it doesn't happen. In fact, you can actually just after the fact, when I pointed it out to them, I've told them, just stack some concrete block up on the footing to catch it. That'll do it. You don't even have to mortar them in, but they don't do it. But on the right, you see where this is probably a 1940s house, and they were brilliant enough to know that you needed to corbel out a couple layers of brick to catch to catch the concrete, and so that concrete is fine. Some of this is just pure laziness. Of course, the builder knows that what I'm saying is true. They just refuse to do it. So on those cases in the new houses, I always put down something like this. I just say, it's gonna happen. Just understand that it's gonna happen. I've told the builder, I've told you, don't call me when it happens. Just expect it. Okay, we're into form concrete. Concrete, when you have forms with reinforcement, it becomes a tough, much tougher task because that reinforcement makes it really hard to get your concrete in all the way down to the bottom of the footing and up through the form. And we use vibrators to make sure that happens. So you got to pour the concrete a little wetter than you'd like to because you can't ram concrete in 8 feet of forms either. So it's just vibrating, but you can vibrate too much too. And there's some bad things that'll happen if you vibrate too much. One is your gravel will start to settle. So you'll have more paste and sand up top and more gravel down below. Or you can actually blow the form out, which happened to one of our guys, a kid that we had working for us. And he was afraid to tell anyone that he had the vibrator stuck. And so he just kept vibrating in the same spot and it blew the form out. So again, this is probably very wet concrete in this particular case, and not vibrated as well as it could have been. This is a form that was, in a semi-state of failure. That's why you have that bulge. Not sure what that one was. I'm gonna move on. There's a saying about concrete, but this is the old saying, but if it ain't cracked, it ain't concrete. Most of the time, in fact, I would say almost all the time, when we see cracks in residential concrete foundations, believe it or not, they're shrinkage cracks. It's just that it wasn't cured properly. It dried out too fast. And that's usually when you get shrinkage cracks. If you were to cure a concrete foundation for, keep it really wet for, 6 or 7 days, you probably wouldn't get any cracks. It's rarely, I mean, if you think about all the steel that's in these things and how overbuilt a concrete foundation is for a house, it's pretty rare that would ever be settlement.
Mike, what's the best material to seal that stuff with? Seal those shrinkage cracks?
I gotta be honest, I don't know. That's not something I get really involved with in the repair. Your guy that did it on the t-shirt you had, he'd probably know better than me.
Well, I was wearing that t-shirt yesterday that said, about the crack man said, I've got to have your permanent crack, have your permanent repair.
Yeah, he's probably very good at it.
Well, the reason it came up is that he said he used to use epoxy, but he doesn't anymore. He's got a more flexible material. But then we had a structural engineer come along and say, well, he still thinks epoxy is the best thing. So I was wondering if anybody had any insight into.
Well, I'll give you my opinion, and this is going to be against the engineer. I mean, the engineer's thinking strength, but like I said, a concrete foundation that's for a house could probably support 50 houses. I mean, the PSI rating is off the chart. You don't have to worry about it from the standpoint of strength or settlement. It's a matter of any moisture penetration. So I don't really think.
And the flexible sealant will move as it continues to crack.
Yep.
Where the epoxy is just going to fail.
Yeah.
Again, you're just going to develop a crack next to the old crack.
I mean, if an engineer is thinking that it's a performance from the standpoint of structure, a concern, he just really hadn't thought this through. He needs to go ahead and pull his calculator out and try again. That's another shrinkage crack. This is clearly concrete that was too wet and not adequately vibrated. That one, the jury's out. There's not a whole lot of porosity to it, but there is some. So that might have been too wet, but it's kind of odd that it has a big air pocket like that. But that's probably, again, too wet and, not vibrated well enough. Not adequate vibration. Again, this one for sure, because see how nicely the paste has formed against the form. They just didn't vibrate everything out and get the bubbles out of it. This is just
You're not writing this stuff up, you just.
No, no. I mean, almost everything I've shown, well, everything I've shown you so far, as far as concrete, to me, it's cosmetic. You know, you rarely see anything big on concrete foundations that's like, oh my gosh, you got to do it again or make some major repair. Again, concrete is incredibly strong. That's too dry there, and it really wasn't vibrated. That's a cold joint. You never want cold joints. They're never good, but they must have had more than one pour and they waited way too long and they didn't bond to each other. Here's where we get into reinforcement. Again, this is the Bluestone Dam up in West Virginia on the New River. Same thing, solid concrete, no reinforcement. And you can see all the lifts as you go down through it. You can see all the pores. There's a lot of pores there. So I underline that to say there's no reinforcement. But then here's a concrete with reinforcement. And what do you think caused this? It's steel rusting, but there's really a couple of things going on here. Number one,
It's too close.
which I think that it's probably wrong to even minimize it to 1.5 inches. They were saying that reinforcement should never be closer to the surface of the concrete than 1.5 inches. I think it should probably be back further than that. But here's where we get into the idea that reinforced concrete limits the life of concrete. Concrete really, it has a half-life of about 100 years. It's still becoming what it's going to become for the first 100 years. And in fact, that's one of the things they said about the Hoover Dam. The Hoover Dam, the concrete is still curing right now. And what it's like 85 years old. But when you put reinforcement in it, concrete starts out as it being kind of steel friendly, but the alkaline and acidity in it changes over the first 6 to 10 years. And it goes from being okay with steel to becoming corrosive as it sets. And then once that happens, then, like you were saying, the steel starts expanding. It can expand up to 6 times its original thickness. And so it starts breaking out the concrete. So the bottom line is, one of the books that I read to prepare for this was saying that concrete, may be able to go a couple thousand years, but reinforced steel concrete in most cases, we'll be lucky if it goes 100 to 150 to 200 years.
So this is what happened to that apartment building in Florida, right? They collapsed.
Oh yeah, well they were really ignoring a lot of stuff there. That when I listened to that, in this one book that I read, kind of centered around a lot of what happened down there, and there was so much negligence in that case. There were things that any of us would have looked at and said, something's got to be done about this, and they didn't do it. Yes, sir.
What about epoxy coated rebar or carbon fiber?
Yeah, carbon fiber. I was reading about that you can do that. You don't see too much of it. Yep. And a coated, yes. That was in that book too. Neither of those is really, I guess they have their pluses and minuses, and there are different mixes of concrete. I'm talking about just straight, normal, modern Portland cement and concrete. But this is why we're getting the concrete failures we are, and why a lot of the bridges look the way they do is because it was a quick fix to build the bridge, but it wasn't the best way to build the bridge, because there are bridges that the Romans built that are still around, that and will continue to be around, and you get what you pay for. So this is moving into retaining walls. So this is a concrete retaining wall, and this has to do with reinforcement again. So that the fact that they've used this design, and they're deciding that the vertical and the horizontal reinforcement with the concrete poured like it is can overcome the need to rotate, or the desire or the pressure to rotate. And it will for a period of time, but when as you can see, all your stress is in that circle here. And when that rebar starts failing, so will that wall. And that's one of the reasons why reinforcement might be, steel reinforcement might be a short-term idea, good idea, but not long-term. Also, you have horizontal joint reinforcement that goes into masonry block walls. I'm afraid these couple pictures here got out of order, and I think they're going to be redundant, so I'm going to move on. I just wanted to show you this because I saw one in the field, and if you'd ever wondered what a precast stairway looks like from the backside, I really had no idea they were this thin, but they are.
That's the stairway to nowhere.
Up in Baltimore, you have 40, 50-year-old concrete condo buildings, and they're all getting fixed, a la the Florida collapse.
Uh-huh.
How do you fix that?
I wish I knew. I don't know.
Because they spend, $2 to $10 million fixing the concrete. And I
Yeah.
have no idea what they're doing.
Well, they're doing a lot of fixing of bridges around here, and I think it's a short-term, Band-Aid. They're still going to have to deal with the long-term problem that, the fixes that they're doing are, my guess is, and I'm really just kind of talking out of my hat even saying it, but my guess is that they're good for 5 more years or something like that. I don't think they're going to really be a permanent fix.
Are they like cutting out low rebar and replacing, or just?
I think mostly what they're doing is cutting out any loose concrete and sandblasting the steel to get it to where it's, clean steel again. And then they put something really high tech back in its place, but who knows how long it's going to last. So I'm going to move on to retaining walls. Yeah. So those photos you just saw, they really were supposed to be out of there. I didn't realize that they were in the place they were. So I'm going to show you some retaining walls here, and I want you to kind of see if you can see a theme throughout the ones that I'm going to show you. They're kind of unusual, and you might not pick up on it, but these are all very old retaining walls that are still plumb and doing their job. And tell me what you see common among these retaining walls. All right, any guesses? And I'll go ahead and don't worry about Mike's. I'll repeat whatever you say, but
Giant aggregate.
Retaining wall kind of slopes back and the hill slopes up.
well, the wall didn't slope back, but you're right on the all of them have a grade over top of the wall, and it's quite considerable. What else is missing? There's something that's missing on every one of these walls. Yep, there's no drainage system. Well, there is, but this is a trick. This is a trick statement. You know where the water goes? Over top of the wall. And what you don't know is that in most of these cases, but let me go ahead and move forward here. So grading, they haven't failed, no drainage system. But this is what you can't see, is most of these are built into the wall in a way that they can't fall forward. The weight is pushing down on the wall, and because the ground goes up high, your frost line is pretty much pushing soil this way. And when it curves down a little bit here, it gives it a little push on the front of the wall, but not much. So it doesn't have to deal with freeze thaw like it would in a flat grade situation where a big portion of soil is pushing against it. It's really pushing out above the wall. And so it doesn't have that stress from freeze thaw. And also the dead weight of the earth on top of it won't let it rotate either. So again, a lot of times the old school guys, they had it figured out, and then we've tried to reinvent the wheel, and we're not doing very well at it. Because this is our option, or this is our choice to try and save some concrete. And again, we're dependent on steel, which will fail. So this is a concrete, or obviously a masonry foundation, but behind it is a drain. There is a drainage system, I think, on this one, but it's flat grade. They didn't tie the brickwork together at the corners at all. And we're gonna find that there's no core fill, no horizontal joint reinforcement. So this wall wasn't even 5 years old. It's probably 4 or 5 years old and it was failing miserably. Yeah, no core fill insulation, the brick aren't tied together. Whoever put it up should have been shot. This retaining wall, I think it actually started out as a dry stack stone wall and they mortared it, which obviously was a big mistake because it used to drain and now it doesn't. And so that was disaster. They should have left it alone. So these are the things that you need to be aware of. And moving on to foundation walls are retaining walls. They don't have to have that same level of thought in how they're built because they have a floor system in a house to kind of help keep them from pushing over. But there are limits to that. But before I go quite there, I'm going to touch for just a moment on solid masonry foundations. You know, when you have brick walls, basement walls that are 3 brick thick, laid in Flemish bond, you know, I can only speak for myself, but I've been doing this for 30 years and I've done about 18,000 home inspections and I've never seen a brick foundation fail unless someone was monkeying around with it. They either did digging behind it or cut a door through it. They did something that affected it, but on its own, you really can't beat a solid brick wall that's all interlocked like that. They almost never fail. So that being said, generally, again, in my experience, the times that I've seen foundation failures, and I think you'll probably say, as I say this, you'll go, yep, you're right. They're usually houses that are between late 1940s and 1970s when concrete block foundations took over the brick foundations. They had hollow cores, they had no horizontal joint reinforcement, and they no steel rebar or concrete. And they failed miserably, and you see it all the time. And that's what these are. This house is probably about 1952, I think, and the walls are coming in pretty good. When that happens, and the walls pushed in, notice there's well, here there's 1, 2, 3 different fulcrum points. And every time that you have one of those points, things are getting picked up. So here are those fulcrum points. So everything is getting raised up. The floor framing is actually getting picked up by each of those 3 fulcrum points. This particular foundation, they did rods way out into the yard with a plate similar to this out in the yard somewhere. So they're using the yard itself. This is probably a better answer. These are your carbon fiber strips. They only work on walls that aren't too buckled in because they're just creating tension that the wall failure can't overcome. But if it's too sharp a bend, that they won't work well.
That new drain tile on the inside
Where's that?
of the wall.
Yeah, they put a perimeter drain system in. They did a lot of stuff there. Yep, so this is just, I already said this. So just in general, when you look at cracks in foundations, whether it be concrete or block work, usually if it's a crack like this, where it's larger at the bottom than top, it's either the footing has buckled downward or the bottom of the foundation is getting pushed in a little bit. And same thing here. And if it's at the top, remember your corners, they're not going to move. So the corners are going to stay plumb. It's the wall inside of the corners that either gets pushed in or the footing has done this. It's far less likely that it's done this. It's really more likely that it's doing this. Then on the backside, there is no crack. It's still tight. It's just gotten pushed in. And so you're looking at the open wound or the open crack on the inside. So these are, let's see here. I wonder if I went backwards a little bit. That might be redundant. Sorry about that, guys. Oh, okay. So here's another, these are some retaining walls that again drain themselves. They're dry stack. So again, if you could pour the concrete monolithic like the masonry, then you could do this and you would overcome those, you would have the gravity holding the concrete into place, and you would be able to overcome any push from the freeze thaw. But when you go to this design here, again, you're relying on steel reinforcement, which will fail. Not really sure I'll understand why these are doubled like that. Pardon me for that. How are we doing on time? Good, because I think I'm done. Yep, I think that's it. Those are just docks planks right there. Which I just saw those one day and just went ahead and took pictures of them. So that's like pre-stressed concrete. Do we have any questions?
The slurry board foundation. You're saying that they're strong enough even though they're excessively watered?
I can't speak for them in terms of the technology behind them, so I better not say anything. I'm sure they're really high in cement. So are you talking about those ones that have styrofoam and?
No, I'm saying like, you see where they're building these, 55 plus communities, they're all on slabs and they come in and they pump the concrete in through a pumper and pour all of them, like big slabs of it. That's full of water. I mean, that's
Oh, yeah. Well, it's, remember that actually what's going on there is it's oh, what's that word called? It's an auger type pump. So it can move pretty dry concrete still.
So they're not liquefying afterwards.
Well, they have to liquefy it some, but probably not as much as you might think, because it's not a matter of, it's not like water. It's being augered and pushed that way. So it can't resist it unless the pipe just plain, blocks. But one thing I didn't touch on, there is a lot of science and a lot of additives that go into concrete. I'm not familiar with them. Mostly what I'm talking about is your just general concrete. But what I do know about concrete, what I've read makes me worry about like that concrete building that was in Dubai, the tallest building in concrete structure in the world. I wonder how long that'll be around. It's like, I hope it's a long time, but I don't know.
The new Trade Center building in New York is pretty close to the Dubai building, and it's built on all those carbon fiber piers.
Okay.
New York's unique because it's got granite right under it on Manhattan Island. So when they drive those down and get them sitting on them, and they have clusters, when they drive the pile, it's a cluster of carbon fiber rods, and then they pour the concrete monolithically all
Yeah.
the way up them, and they just keep stacking.
Yeah, and I read a little bit on that, but not enough to really understand the process and how long it'll last. But I did the same thing that you did. I thought, why can't they make, carbon fiber reinforcement instead of steel? And I'm in reading this book that I did, the last one I did was by an engineer. He touched on that, and also carbon fiber reinforcement that's all through the concrete, which I gather that's a little bit expensive, but as far as performance, I don't know.
I'll tell you what, why don't we get John Bird to let's give John Bird the last door prize, the prize that we didn't have somebody here because.
Okay, I think he had one question though.
On brick walls, when the white's bleeding out of the mortar, that's just the limestone coming out of the mortar.
It could be salt. Actually, salt's used as an accelerator to accelerate setting. And yeah, that's one of its downsides. So I never liked using,
It was just a poor mix job or?
no, it's as water comes through,
Just from that.
it's just like efflorescence. It is efflorescence, but it's salt, calcium mostly.